Hi everyone, thanks for checking out this video. So this is going to be a video about the Lotka-Volterra competition model. This is basically a model that explains like when two species, two populations of animals are in competition with each other for a shared resource that they're both competing over. Also, quick note: this is not the same thing as the Lotka-Volterra predator-prey model. These guys were actually so productive with their careers that they actually have two famous models named after them. So if you guys are looking for the Lotka-Volterra Predator Prey model, I actually have another video about that. So I'll refer you guys to that video. But yeah, this is the competition model, which is something different. Also, one other thing, before we actually get into this, I actually have a quick question for you guys. So my question is, when I'm doing these videos explaining like equations and stuff, do you guys prefer it if I explain on the whiteboard, or do you prefer it if I explain like on the computer, showing the equation like that I typed up on the computer? So if you guys have any preference, please either comment which one you prefer, or I might also make a poll on my YouTube page, so you can either like vote in the poll which one you prefer, or leave a comment which one you prefer. But yeah, basically I want to like make the videos as easy to understand as possible. So I'm making this one on the whiteboard, but like whichever one you guys prefer, I'll just make videos like that in the future. Okay, so now let's get into it. So basically, this video I'm going to explain to you guys the basics of the model, and then there's also going to be a part 2 video that I'm going to make showing you guys how to simulate the model in Python. So that'll be a second video I make after this one. Okay, so before we actually talk about the competition model, I want to do a quick review of the logistic growth model, which is basically how you model the growth of a population of one species where it's growing and growing until it reaches a carrying capacity. So this up here is the logistic growth model, where we have x as the variable representing the level of some population. So I actually have another like longer video about this too. So if you want like a more in-depth explanation, I'll refer you guys to that video. But yeah, the basics is we have some growth rate r multiplied by x. So if we just had this, if we just had dx dt equals rx, then the population would be in a state of exponential growth. But what we actually have is we have this term here, which is it's basically 1 minus x over k, where k is the carrying capacity of the population. So basically, as x gets closer and closer to k, the carrying capacity, this becomes closer and closer to 1, and then we have 1 minus this this quotient, so that this whole term basically will become closer and closer to 0 as x reaches the carrying capacity. So what this looks like basically is the population starts off growing close to an exponential rate, and then it sort of like steadies out and flattens out as it reaches the carrying capacity k. So yeah, this is a pretty standard model for describing the growth of one population when there's a carrying capacity. So basically, the competition model, even though it looks very complicated, it's actually very similar to the logistic growth model, except that the carrying capacity can be filled up by the one species as well as the other species, because they're competing with each other for some shared resource. Okay, so I'm just going to walk you guys through now and explain like what all the parameters are and stuff. So we have two species here. There's X1 and X2. These are the two different animal species, or I guess it doesn't even really have to be animals. It could even be like two kinds of bacteria that are competing with each other or something. But I'll just say animals for now. So we have animal species 1 and animal species 2. They both have growth rates. So R1 and R2 are the growth rates for species 1 and species 2. So at this point, it still looks pretty similar to the logistic growth model. So we have the growth rates here, and if it were just these terms, it would basically be exponential growth for both of them. But then we also have these terms here. So these are basically like the carrying capacity that we had in the logistic growth model, except that like when in the logistic growth model, when you only have one species, it's just that species is what's filling up the carrying capacity. But in the competition model, we basically have the carrying capacity for species one can be filled up by species one as well as species two, because remember they're competing with each other for some shared resource. And same within species two. Species two, it can be filled up by species two as well as species one. Also, you guys probably noticed this, but it's a symmetrical model. So basically, the equation for species two is basically like a mirror image of the equation for species one, except that it's like all of the parameters. There's a different parameter for species two. So like instead of R1, there's R2. Instead of A1, there's A2, and instead of K1, there's K2. But yeah, other than that, it's like a mirror image. Okay, so it's like I said, these are like the carrying capacity terms, similar to the logistic growth model. But in the competition model, instead of just having 1 minus x1 over k1, we actually have in this fraction term here, instead of it just being x1 over k1, it's x1 plus a1 x2. So we have some kind of like scaling parameter a1 that's just a constant parameter, and that's multiplied by x2, the level of the species two. So basically, a1 is a parameter that determines like what kind of effect species two is having on filling up the carrying capacity of species one, so that we can account for the interspecies competition here. And then, other than that, it works the same as the carrying capacity in the logistic growth model. So basically, as this numerator term here on the top of the fraction, as this gets closer and closer to k1, this whole fraction will become closer and closer to 1. So this whole term will become closer and closer to 0. And then that'll decrease like the overall growth rate of the population. And then again, species two, same thing. It's just a mirror image. So we have, rather than just being x2 over k2, we have x2 plus a2 times x1, where a2 is some constant parameter determining the effect of species one on filling up the carrying capacity of species two. Yeah, so I hope you guys are following me at this point. I know it looks like a lot, but I think if we think of it as being similar to the logistic growth model, where we have just some exponential growth term out here, but then it's being affected by like a carrying capacity that's being filled up, and the more the carrying capacity gets filled up by both species, the more the growth rate sort of decreases towards 0 and eventually levels out. Okay, so that's kind of the basics of all the parameters and stuff. So for the next part, I'm going to show you guys how to solve for the steady states. Okay, so if you guys remember, the way we find the steady states of a system of ODEs is to set the differential equations equal to 0. That's because the differential equations are a measure of change in the system. They basically measure the change in the variable with respect to time. So when they equal 0, that means there's no change happening in the system. So basically, to find the steady states, yeah, I've just set both differential equations equal to 0, and we're going to solve for the values of x1 and x2. Okay, so let's just get some of the easy ones out of the way. There's going to be four steady states, four solutions total. 3 of them we can kind of like pretty easily figure out. And then the fourth one we're going to have to actually do a bit of algebra to solve for. But okay, let's just get the easy ones out of the way. So the first easy one is just 0, 0, the trivial steady state. If there's 0 of x1 and 0 of x2, 0 of both species, that means there's nothing happening in the model, nothing happening in the ecosystem. So that's kind of a trivial steady state, but I'll write it down anyway, just because it is a steady state. But yeah, 0, 0. That's the first one. And if you guys have to like check and make sure that makes sense mathematically, we can see that would make both of these terms 0. So that would be 0 multiplied by whatever this is, and 0 multiplied by whatever that is, and then that of course would equal 0. Okay, so let's think about the next two. Uh, so let's think about what happens if we have 0 of x1. Could we have 0? Like, what would happen? What would this equation look like if we had 0 of x1? So if we have 0 of x1, this just becomes the logistic growth model for x2. Because if you guys see, this term here would multiply out to 0. So we would just have r2 times x2 times the quantity 1 minus x2 plus 0, so ignore that, over k2. So if we have 0 of x1, then this equation for x2 just becomes the logistic growth model. So in that case, another solution is 0 of x1 and k2, the carrying capacity of x2. Because if you guys remember the logistic growth model, the non-trivial steady state is the carrying capacity. And if you guys have to check and make sure that makes sense mathematically, just think about this being 0, this being k2, and then this whole thing equals 1. 1 minus 1 is 0, and then it equals 0. And then this one equals 0 just from x1 being 0. Okay, and then so you guys might have guessed from that the third steady state is going to be the reverse. So this will be k1, the carrying capacity for species 1, 0. And then that's the same thing. If we have 0 of species 2, then this whole equation becomes the logistic growth model for species 1, because this a1 times x2, this will just be 0. And then this whole thing just becomes the logistic growth model. And then like the non-trivial steady state for the logistic growth model is the carrying capacity. So our third steady state is k1 for x1 and 0 for x2. Okay, so that's basically all of the easy ones. The last one we have to actually do a bit of algebra to solve for, but it'll be okay. We can do it. It's not going to be that bad. Okay, so the way we're going to do this is we're going to think about these terms. What will it take? How can we set x1 and x2 so that these two terms will both be 0? And if we get these to be 0, then 0 multiplied by whatever these are, that will also make the whole thing 0. So I'm gonna say, let's just start with x1. Let's just try to write an expression for x1 in terms of x2 and the parameters. So I'll say 0 equals 1 minus x1 plus a1 x2, all of that over k1. Okay, move this over to the other side. So then we have x1 plus a1 x2 over k1 equals 1. You guys follow me so far? Hopefully this is just some pretty basic algebra so far. And then multiply both sides by k1. So then we have x1 plus a1 x2 equals k1. And then lastly, subtract a1 times x2 from both sides. So we get x1 equals k1 minus a1 x2. And now we have an expression for x1 in terms of x2 and the constant parameters. Okay, so let's take a look at this side. So I'm gonna skip a bit of the algebra here because we know that these are symmetrical. So whatever we've said for x1, we can say the same thing for x2 in terms of x2's its own parameters. So I'm gonna just take this line here and I'm gonna say the same thing for x2. And if you guys want, you can actually do the algebra out from x2 and prove to yourself that we can get to this line for x2. But for now, I'm just gonna copy this line and say x2 equals K2 minus A2 times X1. Again, you guys can reach this from the algebra here if you want to, but yeah, I'm just gonna say this for now. And then what we do here is we need to plug in the value we found for x1. So we're gonna plug this value for x1 in right here, and then we'll have the whole thing in terms of the parameters and x2. So this is going to be x2 equals k2 minus a2, and then here's where we're plugging in this expression for x1. Okay, so k1 minus a1 x2. Okay, so now it's just a matter of computing this out here to get the answer in like a nice format. So the next line is going to be x2 equals k2 minus a2 k1 minus a1 plus, right? Yeah, plus a1 a2 x2. Okay, so let's try to get all the x's on the same side and everything else on the other side here. So we're gonna have okay, yeah, I'm gonna move this term over to the other side to make it x2 minus a1 a2 x2 equals everything that's left, k2 minus a2 k1. Okay, and then we're gonna take x2 out of this, and we're gonna write this as x2 times 1 minus a1 a2 equals k2 minus a2 k1. And then for the last step, just divide both sides by 1 minus a1 a2. So then we have x2 equals k2 minus a2 k1 over 1 minus a1 a2. Okay, so this is the solution for x2 in terms of the model parameters. So if you guys have time and you want to do the algebra, what you would actually do to really solve for x1 is you would take this value and just plug it back in here, and then compute out what this gives you for x1. But I'm not going to do that on the board because that will be a lot of algebra and I don't have space. So I'm just going to ask you guys to take my word for it that since like we said, it's symmetrical, like the equation for x2 is just a mirror image of the equation for x1. The solution you will get for x1 if you do that is just going to be like basically this, but with the opposite parameters, with all the parameters for x1 rather than x2. So yeah, this will just be k1 minus a1 k2 over 1 minus a1 a2. That's the solution for x1. Yeah, again, if you guys don't believe me, like I encourage you to do all the algebra out yourself, just for like good practice. Just plug this back in for x2 here and compute this out, and that's going to give you this solution here. Yeah, so this is our fourth steady state. This is like the non-trivial one, I guess. These ones are all kind of somewhat trivial, I guess, but yeah, this is the last steady state. Yeah, so that's really all I have for you guys for this video. The next video is going to be about how to implement this model in Python to do a simulation of the ODEs. But yeah, that'll be a separate video, I think. Yeah, if you guys have any questions, just let me know in the comments. Also, please don't forget, if you have a preference of whether you prefer the whiteboard explanation or the like typed up equation on the computer explanation, please either leave a comment saying which one you prefer, or vote in the poll on my YouTube page. With And then whichever one people prefer, I'll make videos like that in the future. Um, yeah, so thanks for watching, and see you guys next time.